Hello, I am Michael Oliver, and this is Module 3, where I will be looking at logistic regression and comparing it to a normal OLS model. First, I wanted to look at my variables, though. For this module, I am looking at chocolate as our dependent variable and sugar content, price, and fruitiness as the predictors. Sugar content and price are both on a continuous scale, and they are both in percentiles. So price, the data for price and sugar content will be percentiles compared to the other. These are all candy bars, so the sugar content price compared to the other candy bars. Whereas chocolate and fruitiness are both on a categorical scale, so it is yes or no, is chocolate or is not chocolate, and is it fruity and is it not fruity. All right, so now that we understand that, it's time to get to the actual model. So first we have the general linear model. We see here that we have y, in this case would be chocolate, would be equal to the b value for price, the b value for sugar content, and the b value for fruitiness, as well as the b value for the intercept. Looking at this and getting the output, we see that price is significant, as well as whether or not it is fruity. Price having a b-value of 0.39 and fruity having a negative b-value of 0.64, as well as having intercept of 0.53. All three of those are significant, so I'll talk about that in a second. And we see that sugar content is not significant, has a b-value of 0.01, so there's almost no relationship, and it is not significant at all. But what do the b's values actually mean? Well, they mean practically nothing, because this model does not take into account that our dependent variable is categorical. It expects a continuous variable, so these b's are, the p-values are inflated, they don't actually make any sense, and the b-values, because our dependent variable is either chocolate or not chocolate, and these are assuming that there is a range between chocolate and not chocolate, even though that's not true. So we can't really understand these b-values. What we can do, though, is look at the diagnostics before we move any further. So we see that on the top left, we see that the normal QQ plot more or less expected residual results, except for a little bit on the tail end on the left side. That is not super uncommon, so I'm not really afraid of that. We do see that the residuals versus fitted graph on the top right is pretty messed up, but I kind of expected that because it is a categorical variable, which moves us to the bottom left. We actually see, as we would want, independent identically distributed for our dependent variable. It is not perfectly identically distributed, it's not perfectly symmetrical, but it's within reason enough for me personally in order to continue moving. We also see that Cook's distance is not very large for any of our data points, and there's no real leverage held by any one data point that might affect everything else. So next, we also look at just the basic relationship between our dependent and predictors. We see that price has a medium positive relationship. Sugar content's pretty weak. There's no real relationship there. While fruitiness has a negative relationship. Again, these b values don't necessarily mean anything, but I wouldn't expect these relationships in nature to change too much. Next, though, in order to actually get b-values that do make some sense, we want to look at the generalized linear model, different than the general linear model. Same basic equation, though. We have a b-value for price, sugar content, and fruitiness, or whether it is fruity or not, as well as an intercept. But these b-values are actually going to be in odds ratios. In fact, they will be in log odds ratios initially, but I will show it as odds ratios. What this means is that an odds ratio is the probability of the event happening versus over the probability of the event not happening. This is different than the percentage probability, which is the probability of an event happening over the probability of all other outcomes, all total outcomes possible. So these two are just a little bit different. I'll talk a little bit more about them in a second. But first, we see that our results, listed here as odds ratios, which I'll talk about in a second, are actually significant still. We see that the results for the b-value for price and the b-value for whether it is fruity or not are both significantly different from 0, or in this case from 1. So we see here that the price has a b-value of 25.6-ish. That means that there's about a 25.6 to 1 odds that your dependent value will be chocolate, in this case, will be chocolate if the price increases. So as the price increases, your odds go up relatively more on a scale of 25.6 to 1. This is in contrast to sugar, which has b-value of 1, which means it's about 50-50 odds, about a 1-to-1 relationship. So your odds do not increase, and there is no real relationship or relative increase in probability on your dependent variable. And this is different than whether it is fruity or not. Fruity has a 0.01 b-value, which translates to about a 1 to 100 odds for the chocolatiness to increase, or whether it is chocolate or not, to increase if fruity increases. Again, I'll explain this a little bit more. So, in order to understand these estimates, we have to talk about the three different forms that these estimates come in. First is the log odds ratio. These log odds are odds ratios, as I explained before, but on a logarithmic scale using a base of e, a natural log. This is because log and probabilities follow a exponential curve with a natural base towards its asymptote of e. Basically, this makes data that is naturally curvy look relatively straight and gives us a number that is relatively easy to understand. But it's only relatively easy to understand. It's not that easy. So in order to translate it into something that's even easier, we exponentiate it. We make e to the power of whatever the estimate is. So in this case, our log odds ratios for fruity was negative 4.53, and for price, it was 3.24. We put that over e and we figure out what the result is. So for fruity, the odds ratio, pure odds ratio, is actually 0.01, whereas for price it's 25.6. This is what I was showing you before. The results that I used already were showing odds ratios instead of log odds ratios. But in order to get that into actual percentages, you have to transform it using an equation that goes from the probability of an event happening over it not happening into the probability of it happening over all of the events. This gives us estimates of fruity being negative 99% and price being 96.24%. What this tells us is that for every 1 unit increase in the probability of it being fruity, it is categorical. So we have to take that into account. So for every 1 unit increase of the candy bar being fruity, you have relative odds compared to the unit before go down 99%. So it becomes the probability of it being chocolate decreases for every increase you have in the probability of it being fruit. For every 1 unit increase in the price, which in this case is a percentile, so every 1 unit increase in price percentile, your relative odds go up 96.2% compared to what it was previously. So as your price goes up, the probability of it being chocolate also goes up. We see that here as well. I included the sugar content in there, even though it is no relationship. We see that it's basically nothing, so we can just ignore it. But we see on the left that price has a positive relationship, and that is due to the nature of odds ratios and the way probabilities work, because it is a relative increase. It is relative for the one before it, so each slope slightly changes as the x-axis increases. So we see that change is positive for price and negative for fruity. I did include the data points for the fruity, and they are kind of clustered, but just know that it's for visual, and that in actuality it is either fruit or a 0 or 1 for fruit or no fruit. They are not actually randomly clustered around those areas for fruit. All right, so a little bit more in-depth look at that. So we see that as price increases, the probability of it being chocolate also increases. It plateaus a little bit around 0 and around 1 for price because the relative odds can only go up so much. It is a asymptotic relationship in nature, so there's only so much of a chocolate probability that it could be. But we see in general that it is a positive relationship, especially around 0.5. There's that point in the graph where slope is just a little bit more than normal, a little bit more than all the other points. That is when the probability greatly increases for the price percentiles. And we see a reverse trend of that for fruity. It's slightly different. The maximum probability is only about 0.75, but we see that it is in fact a negative relationship. So as the probability of it being fruit goes up, the probability of it being chocolate goes down. So fruit not likely to also contain chocolate in a candy bar. But before anything else, I also wanted to test the interaction. I erased the sugar content since we proved twice that it was non-significant and did not matter, and I replaced it instead with an interaction of fruit and price. This interaction was non-significant in nature, and this is a generalized linear model using logistic regression, so these estimates are in odds ratios again. But we see that not only was the interaction between the two variables non-significant, it took away significance from the fruit variable as well. What I assume this is because it drew variance away from the raw fruit predictor, made it non-significant, and the leftover variance was just attributed to price. So I do not think that this and the fact that the interaction is not significant, I do not believe that this is a significant model as well, either. And that is the end. Thank you.